Energy stores and systems. A system is an object or a group of objects. Energy is transferred by heating, mechanical work, electrical work, or radiation, and energy is measured in joules J. Key examples of energy store changes. An object that's moving upwards has kinetic energy transferred to gravitational potential energy. An object that's moving and hits another object has kinetic energy that's transferred to thermal energy and sound energy. An object that's accelerating by constant force has chemical energy that's transferred to kinetic energy. An object that's slowing down has kinetic energy that's transferred to thermal energy, such as when a car brakes. Boiling water with a kettle has electrical energy that's transferred to thermal energy. The kinetic energy equation is equal to a half times mass times speed squared, or EK equals a half mv squared. Mass is measured in kilograms, speed is measured in meters per second, and kinetic energy is measured in joules. Don't forget to square the speed. Elastic potential energy is found in objects that can be stretched or squashed, such as springs. The equation is a half times spring constant K times extension squared, where spring constant is measured in newtons per meter, extension is measured in meters, and elastic potential energy is measured in joules. Gravitational potential energy is found in objects that are risen above a certain height. The equation is GPE equals mass times gravitational field strength times height, or GPE equals m times g times h. Remember, on Earth, the gravitational field strength is actually 9.8 newtons per kilogram. Specific heat capacity is the amount of energy required to raise the temperature of a 1 kilogram of substance by 1 degree Celsius. The equation is change in E, or change in energy, equals mass times specific heat capacity C times change in temperature. Remember that specific heat capacity is measured in joules per kilogram degrees Celsius. Power is the rate at which energy is transferred, and it has two equations. Either power equals energy divided by time, or P equals E divided by T, or it could be the rate at which work is done. So power is equal to W, work done, divided by time. Remember that energy and work done are both measured in joules. Power is measured in watts, and time is measured in seconds. Conservation of energy. Energy cannot be created or destroyed, only transferred and stored or dissipated. In a closed system, no net energy changes. Some energy can be wasted as less useful stores, such as in a light bulb. Its main job is to release light energy, but some energy can be transferred as thermal energy, making the light bulb hot. Energy transfers. Energy is dissipated to surroundings by heating. Ways to reduce thermal energy transfer. First is lubrication, so there's less friction and less thermal energy transfer. 2 is thermal insulation, which reduces conduction, e.g., double glazing, loft insulation. Lower thermal conductivity equals good insulation. Efficiency calculations. Efficiency measures how well devices transfer energy to useful forms instead than wasting it. It's expressed as either a decimal or a percentage. So efficiency is equal to useful output energy transfer divided by total input energy transfer. Or efficiency is equal to useful power output divided by total power input. National and global energy resources. Fossil fuels like coal, oil, and natural gas are non-renewable. Nuclear fuel is non-renewable. Biofuels, wind, hydroelectricity, geothermal, tidal, waves, and solar are all renewable sources of energy, which means that they can be replenished within their lifetime. However, fossil fuels are finite resources and cannot be replenished in their lifetime. Whilst these energy resources are useful for transport, electricity generation, and heating, they are not without fault. For example, solar and wind power have low reliability because they are weather dependent. Also, fossil fuels release carbon emissions, which can have negative environmental impacts. Nuclear fuels can lead to nuclear disasters if not maintained, and can lead to high decommission costs of their stations. The specific heat capacity required practical investigates how different materials heat up at different rates. First, measure the mass of the metal block. Second, insert a heater with a drop of oil and a thermometer. Third, record the starting temperature. Fourth, heat the block for a set time, such as 10 minutes. 5, record the final temperature. 6, repeat and calculate the mean. Calculate the energy transferred using the equation, which we discussed a few slides ago. You want to change the metal block to investigate different materials. So this means that this is the independent variable. The dependent variable is the temperature increase of the metal, and the control is the mass of the metal block, how long you heat the metal block for, and the current supplied. Apparatus needed is a metal block, an electric heater, a thermometer, a power supply, a top pan balance, a stopwatch, and a thermal insulator required practical for triple science only. Good insulators reduce energy transfer by heating, so the best insulator will have the smallest temperature decrease. First, add a set volume of hot water to a container. Wrap the container in insulating materials. Record the temperature at the start. Leave for a fixed time such as 10 minutes and measure the final temperature after this. You want to then calculate the temperature decrease. The apparatus you need is a container, different insulators, a thermometer, a stopwatch, a measuring cylinder, kettle, and water. The independent variable is the thickness or layers of the insulator or the type of insulator you use. The dependent variable is the temperature decrease, and the control variable is the container and the set time and the volume of water used. Next topic, electricity. Here are all the circuit symbols that you could get asked to recognize and draw and use when drawing your own parallel and series circuits. Pause the video to see if you can recognize any of them and test yourself as well. Let me know how many you got right. Electric current is the flow of electrical charge. Charge Q is equal to current I times time T. Charge is measured in coulombs, current is measured in amps, and time is measured in seconds. The greater the resistance of the component, the smaller the current for a given potential difference or voltage across the component. So potential difference or voltage is equal to current times resistance. Remember, potential difference or voltage is measured in volts, current is measured in amps, and resistance is measured in ohms. Resistors. Different devices can have different current, voltage, and resistance. These characteristics can be plotted graphically as IV graphs. The first is an ohmic conductor. Current is directly proportional to voltage across a resistor at a constant temperature. Resistance of lamps, diodes, thermistors, and LDRs is not constant. So the second IV characteristic graph you need to know is a filament lamp, and it looks like this. Resistance increases as the temperature increases. The third IV characteristic graph is a diode that you need to recognize. Current flows in one direction. In the reverse direction, the resistance is very. Resistance in other components. Thermistors, resistance decreases as the temperature increases, and a use of a thermistor is in thermostats. LDRs, resistance of an LDR decreases as light intensity increases. A use of an LDR is turning lights on when it's dark. Let's compare series and parallel circuits. In a series circuit, the current is the same through each component, whereas the total potential difference is shared. Total resistance of two components is the sum of the resistance of each component. For example, R total or total resistance is equal to the resistance of the first component plus the resistance of the second component. In a parallel circuit, the potential difference is the same through each component, whereas the current is shared, and that is the total current. Total resistance of two resistors is less than the resistance of the smallest individual resistor. Let's look at voltmeters and ammeters. A voltmeter measures potential difference or voltage in a circuit and is connected in parallel to the component you're investigating. An ammeter measures the current and is connected in series. Mains electricity is alternating current. Alternating current, AC, is current that changes direction, whereas DC or direct current is current that goes in one direction. Domestic electricity in the UK has a frequency of 50 Hz and a voltage or potential difference of 230 volts. The 3-pin plug in the UK for electrical devices is as follows. Every wire in the 3-pin plug has an electrical insulator that helps us identify each of the wires. The brown wire is the live wire and has alternating potential difference of 230 volts. The yellow-green striped wire is the earth wire and is often known as the safety wire because it has 0 volts. The blue wire is neutral, it has 0 volts and completes the circuit. Power calculations that you need to know. There's two. The first is P equals V times I, or power equals voltage times current. The second is P power equals I squared, or current squared, times resistance. Remember, resistance is measured in ohms, power is measured in watts, voltage is measured in V, or volts, and current is measured in amps. Next is energy transfer in everyday appliances. So work is done when charge flows. Domestic devices transfer energy from batteries and AC mains to kinetic energy in terms of motors or objects that move, or thermal energy if there are objects that get hot. Equations you need to know equals energy equals power times time, or E equals P times T, and energy equals charge flow times voltage, or E equals Q times V. Remember, charge flow is measured in coulombs. The national grid is made up of cables and transformers linking power stations to consumers. Transformers are found from power stations to the home. Step-up transformers increase the voltage as the electricity goes from the power station. Step-down transformers help decrease the voltage as it enters the home. This reduces current flowing through cables, so more of an efficient way of transferring electricity and reducing the wasted energy that would otherwise heat up the wire because of the wire's resistance. Static electricity, triple science only. Insulators, when rubbed together, become electrically charged, and this is due to the movement of electrons. An insulator that gains electrons becomes negatively charged, and an object that's an insulator that loses electrons becomes positively charged. Static electricity is an example of a non-contact force. If two oppositely charged objects interact, they have attractive forces, whereas the opposite is the case for two of the same charged particles, you will have a repulsion force. Sparking is an example of an electrostatic phenomena. Charged objects create an electrical field around themselves in a radial field. The objects in the field experience a force, and the closer that object is to the field, the stronger the force. Remember, uniform fields are parallel. Resistance of a wire required practical. Resistance depends on temperature and length of a wire and circuit arrangement. First, set up the circuit with an ammeter and voltmeter. Measure the current and voltage. Change the length of the wire or the circuit arrangement. Record the readings and calculate the resistance using R equals V divided by I. The variables include control variables, the wire temperature, the thickness of the wire, or the metal of the wire. The dependent variable is the resistance, and the independent variable is the length of the wire. IV characteristics required practical. To investigate how current changes with potential difference, resistors at a constant temperature follow Ohm's law. First, set up a circuit with a power supply, resistor, ammeter, and voltmeter. Change the potential difference using a variable resistor. Then record the current and voltage. Repeat for different voltages. Plot the IV graph. The variable for this is the control variable, the wire temperature and length. The dependent variable is the current, and the independent variable is the potential difference. Next topic, density is mass per unit volume. It has the equation density equals mass divided by volume, where density is measured in kilograms per meters cubed. The particle model shows density. Solids have a regular arrangement and are densely packed and vibrate at fixed positions. Liquids are irregular and flow. Gases are also irregular and flow with more spaces, and therefore there is decreasing density from solids to liquids to gases. Changes of state, mass is conserved, and these are physical changes. So melting is solid to liquid, evaporation is liquid to gas at the surface, boiling is liquid to gas which has bubbles throughout, freezing is liquid to solid, condensing is gas to liquid, sublimation is solid to gas, no liquid state, and deposition is gas to solid, no liquid state. Internal energy is the energy stored by the atoms and molecules in a system. Internal energy is calculated by kinetic energy plus the potential energy. By increasing the temperature, you increase the internal energy or you change the state. Specific latent heat is the energy needed for 1 kilogram of substance to change state with no change in temperature. Energy change in state is equal to mass times latent heat, or E equals M times L, where energy is in joules, mass is in kilograms, and latent heat is in joules per kilogram. Specific latent heat of fusion is solid to liquid. Specific latent heat of vaporization is liquid to gas or vapor. Heating and cooling graphs are shown as follows. Be careful to note where the solid, liquids, and gases are on each, and remember you can identify the melting, boiling, condensation, and freezing points. Particle motion in gases. Gases have a constant random motion, and gas temperature is directly linked to kinetic energy. Changing the temperature of a gas at a constant volume changes the pressure exerted by the gas. Pressure in gases triple only. Gases can be compressed and expanded by pressure changes. Pressure produces a net force at right angles to the container by gas particles. Pressure in pascals times volume in meters cubed is equal to a constant, or PV equals constant. Increasing pressure in gases triple and higher only. Work is the transfer of energy by a force. Work on a gas increases the internal energy and increases the temperature. A key example is a bicycle pump that you expand and increase the amount of gas and therefore increase the amount of pressure. Let's look at the required practical for density. Density of regular objects is first calculated by measuring the mass using a top-pound balance and recording it. You then want to measure the dimensions of your object using a ruler, or more accurately, a vernier caliper or micrometer. You then want to calculate the volume of that object and then work out density, which is density equals mass divided by volume. For irregular objects, it's kind of the same, but just slight difference in the volume. So you start off by measuring the mass using a top-pound balance and recording this. You want to measure the starting volume of water and place that irregular object into the water and measure the new volume. The volume of water that's been displaced is the object's volume. You use the same equation, density equals mass divided by volume, to calculate density. Let's look at the last topic, atomic structure. Atoms have a radius of 1 times 10 to the minus 10 meters. The nuclear radius is actually less than 1/10,000th of this size. The proton has a positive charge and a neutron has no charge, and they are found in the center of the atom called the nucleus. This is where most of the mass is found. Electrons actually orbit the nucleus in orbital shells, and they have a negative charge overall. Electron arrangement can be changed by absorbing electromagnetic radiation, so they have a higher energy level, which means it's further from the nucleus, or by emitting electromagnetic radiation, which means they have a lower energy level, which means they're closer to the nucleus. So the mass number is the number of protons and the number of neutrons. The atomic number is just the number of protons or the number of electrons. Remember, the electron number is the same as the proton number, so the actual atom has no overall charge because their charges cancel out. Isotopes are atoms with the same number of protons but a different number of neutrons. The atomic model has changed over time. Dalton thought that atoms were solid spheres. Thomson thought that the atom was like a plum pudding, or the plum pudding model, so a ball of positive charge with negative electrons embedded within it. Rutherford did an alpha scattering experiment and discovered the nucleus, or most of the mass is found in the center. Bohr discovered electrons in fixed shells, and Chadwick discovered the neutron. Radioactive decay is a random process. Some atomic nuclei are unstable and they can emit radiation to become more stable. Activity is actually the rate of decay, which is measured in becquerels, and the count rate is the number of decays each second, which can be recorded and detected by Geiger-Müller tubes. Nuclear radiation is emitted from the nuclei in different forms. The first is alpha, which is 2 neutrons and 2 protons, or a helium nucleus. Beta, or beta decay, is a high-speed electron ejected from the nucleus as a neutron, which turns into a proton. Gamma is an electromagnetic wave of radiation, and neutrons are also emitted too. Alpha is highly ionizing, beta is less ionizing, and gamma is the least ionizing. However, in terms of penetration, alpha can be stopped by skin or by paper and can only travel around 5 centimeters in air. Beta radiation, however, can be stopped by 3 millimeters of aluminium foil and can only move around 1 meter in air. Gamma is the most penetrating because it's stopped by concrete or lead, and in air can move around or just over 1 kilometer. Nuclear equations represent nuclear decay. Remember, alpha is a helium nucleus. So if you have substance X, you can see that the difference between the mass number is a difference of 4, whereas the proton number or atomic number is a difference of 2. Beta decay doesn't change the mass number, but it does change the proton number. So be careful with this. These are just some examples, but you could be given any examples to balance. Half-lives. Remember, decay is a random process. So a half-life is the time it takes for the number of nuclei of an isotope in a sample to half, or the time it takes for the count rate or the activity from a sample containing the isotope to fall to half its initial level. Net decline radioactive emissions. This is for higher tier students only. Feel free to skip ahead if you need to. How much of a sample remains expressed as a decimal, fraction, or ratio. So for example, a sample has a half-life of 4 years. How much of a 100-gram sample is left after 12 years? So you first need to calculate 12 years as a half-life. So 12 years is 3 half-lives because you've done 4 times 3, which is 12. You then want to use this number of 3 half-lives to work it out as a fraction. So a half cubed is 1/8 as a fraction. Or you could express this as a decimal. So 1/8 of 100 grams is 12.5 grams, or as a ratio, it's 100 to 12.5. Radioactive contamination. Objects can have unwanted radiation either by irradiation or contamination. Irradiation is when an object is exposed to radiation but not itself radioactive. It stops when the sources of radiation are removed and can be blocked. Contamination, on the other hand, is when radiation is within the object and the object becomes radioactive as it's exposed. It can't be blocked and it's difficult to remove. The next few topics are for triple science only. Background radiation is around us all the time, from cosmic rays to rocks to man-made items. Half-lives and radioactive isotopes. Isotopes have a wide range of half-lives. Short half-lives are short exposure, intense exposure of radiation, bursts of radiation but with immediate hazards. Long half-lives, however, are long-lasting exposure, less intense, but they can stay around for years, if not decades. Uses of nuclear radiation, specifically in medicine, can be used for organ function. Radioactive isotopes can be used as tracers to see the function of kidneys or other soft tissues. A gamma camera can be used to show the amount of radiation that is detected, to show if there are blockages, if there is less radiation emitted. They can also be used to control or destroy cancerous tissues through radiotherapy and by ionizing and destroying the DNA of cancer cells. All isotopes that are used are non-poisonous. Nuclear fission is the splitting of a large or unstable nucleus to release lots of energy, such as uranium or plutonium nuclei. The unstable nuclei is bombarded with neutrons, and therefore you produce 2 of the same sized, smaller nuclei, and they have kinetic energy, so move away. You also have 2 or 3 more neutrons that are released, and these can go on to produce chain reactions with the nuclei that have formed. Gamma rays are also released as well as energy. Nuclear fusion is the joining of 2 light nuclei to form a heavier nucleus. Some of the mass is converted into energy as a result. Fusion is found in the sun. And that's it from me today. I've been the GCSE science teacher and you have been curious. I hope you enjoyed this video. Thank you so much for all of your support on my previous videos for chemistry and for biology paper 1. Paper 2 content will be coming out soon. I hope your exams are going really well. Feel free to subscribe if you haven't already, and welcome if you're new. It's amazing to have you here. Feel free to also share this with someone else, especially as it's middle of the exam season now. You're halfway through your GCSE sciences, which is so exciting. I hope you're all doing well. Take care, and I'll catch you in the next one.